In this video we're going to introduce Maclaurin's formula, which gives us a way of creating a polynomial approximation to a formula which is not itself polynomial. Okay, so this is Maclaurin's formula, and as you can see it's a sequence that just continues here, or a series that just continues here, and basically what happens is we need to find out the value of f of 0, the value of f dash of 0, f double dash of 0, and so on. Now obviously the formula must exist at 0 if we're going to use this formula, because if it doesn't exist it's not going to work. So for instance we can't use this to find the expansion of log x because obviously log of x does not exist. And also this is really important, the more terms we have the better our approximation. So if we just do it for the first term then it's not really going to be that useful. The more we have the better it's going to be, and typically speaking you're only going to be interested in the first 3 or 4 terms. Okay, so where does that formula come from? Well, considering we've got a function f of x which is not a polynomial and we want to represent it as a cubic. Now this idea we can expand to be an infinite series, but we're just going to look at a cubic at the moment. Now let's see, we can differentiate that cubic to get this function, we can differentiate again to get this one, and we can differentiate a third time to get this one. Now the point is if this g of x is going to have similar properties to f of x, then at x equals 0, g of x, we want it to equal f of x. So g of 0 is going to, well, this term goes, this term goes, this term goes, equals a, and we know that's got to equal the same as f of 0. More importantly for us, a equals f of 0. And then doing the same thing at 0 for g dash of x, we end up with b for here, and we end up with b equals f dash of 0. And then doing it for g double dash, the same thing, so we get this, and actually that's going to give us that c equals f double dash of 0 divided by 2. And here we're going to end up with, using the same idea, that d equals f triple dash, or the third differential of f, divided by 6. So substituting these values of a, b, c and d back into g of x, we end up with g of x equals this function here. And you can see 2 is the same as 2 factorial, 6 is the same as 3 factorial. If you had done this for a quartic, you would have ended up with the next term not 1 over 6 but 1 over 24, which is 4 factorial. And this is really where Maclaurin's formula comes from. Okay, let's have a look at an example. Say we want a polynomial approximation to e of x. Well, f of x is e of x, so f of 0 is 1. Nice, f dash of x is e to the x, so f dash of 0 is 1, and so on. They're always going to be 1, because that's the nice thing about e of x. So substituting in those values of 1 for f of 0, f dash of 0, and so on into this formula here, gives us this formula for a polynomial approximation of e of x. And you can see here the first 4 terms for e of x, and try that for some values close to 0 and see how close they are to the actual function e of x. Now I said we couldn't do an approximation for log x because, or natural log of x, because it doesn't exist at x, but we can do it for x plus 1 because obviously natural log of x plus 1 does exist at x equals 0. So we're going to substitute in 0 to f of x, we're going to differentiate and then substitute in 0, we're going to differentiate again, substitute in 0, differentiate again and substitute in 0, and hopefully we can see what's happening now that we get this general term here. Typically speaking, we're not going to be using the general term because we're after an approximation we only want so many terms. So here we go, we have our general formula here, and we're just going to substitute these values in, and you get this really simple formula for the natural log of x. It's x plus x squared over 2, sorry, minus x squared over 2 plus x cubed over 3. This will be minus x to the 4 over 4 plus x to the 5 over 5, and so on. Okay, to end, I just want to show you the approximation in practice. So what I've got here is the green line is the line y equals sine x, and what I'm going to do is we're going to gradually use more and more terms of the Maclaurin expansion. So I started off with y equals sine x, which gives this red line, and you can see that really close to 0, even that's not a bad approximation. If I add in the next term, then and don't forget that's the red line here, you can actually see this is pretty good, even as far up as round about 0.6ish. So we've added in that next term. Let's add on one more term. Where does that get us? But we're almost right now, almost as far as a half pi. It's looking pretty good, and it's coming down for the next term. Let's bring in the next term now, and it's not made a massive difference, but certainly we're getting close to 3/4 pi, and the approximation is pretty good. And then let's bring in the next term, and almost as far as pi, I would say it's a pretty good approximation. It's coming down and starting to come back up. And the more terms that we add in, then the better the approximation of our polynomial is going to be to the original function. In the description below you can find a link to a worksheet that has questions that you can try on your own. I hope you found this video helpful. Staying in field with Winfield.